A streak of light tears across the sky and is gone in a heartbeat. That fleeting moment holds a profound cosmic secret, a glimpse into the universe's ultimate speed race. We are surrounded by objects moving at velocities so immense they defy human intuition, from ghostly particles smaller than an atom to entire galaxies hurtling through the void. Over the next 50 facts, we will unravel the mysteries of these cosmic speed demons, revealing how they bend the very rules of reality and challenge our understanding of physics itself. You will discover why nothing can outrun light, how stars are catapulted into the abyss, and what happens when space itself expands faster than anything can travel. What single force do you believe sets the ultimate limit for speed in our cosmos? That ultimate limit is not a suggestion but a fundamental law woven into the fabric of reality. Nothing in the universe can travel faster than light in a vacuum, a staggering 299,792 kilometers per second. This is not merely a speed limit, it is a consequence of the very geometry of space and time, as revealed by Einstein's theory of relativity. As an object moves faster and faster, its mass does not simply increase a little, it grows towards infinity. Imagine trying to push a shopping cart that becomes heavier with every step you take. At first, it is easy, but soon it feels like you are pushing a car, then a truck, then an entire mountain. To reach the speed of light, you would need an infinite amount of energy to push that infinitely heavy object, a feat that is utterly impossible. This cosmic speed limit is so unwavering, so constant, that it is used to define the meter itself, the very unit of distance. This single number is the unbreakable rule against which all other cosmic velocities must be measured, the silent governor of every motion from the smallest particle to the largest galaxy. So what entity is gifted with this ultimate velocity? The answer lies in particles that are born racing. Photons, the fundamental particles of light, are the universe's massless marathoners. They are unique because they possess zero rest mass. Think of rest mass as the inherent heaviness of an object when it is sitting still. A baseball has rest mass. You have rest mass, but a photon has none. It is pure energy in motion. This lack of any intrinsic weight is the secret to its unparalleled speed. A photon does not need to accelerate. It bursts into existence already moving at 299,792 kilometers per second. From its very first moment, it is at the cosmic speed limit. Consider the journey of a single photon born in the sun's core. It begins a frantic, zigzagging escape through the dense solar interior. This leg of the trip is not a straight shot. It is a chaotic pinball game against a storm of other particles. This process alone can take over 100,000 years. But once that photon finally breaks free from the sun's surface, its path clears. The rest of its voyage to Earth is a silent, straight sprint across 93 million miles of near-perfect vacuum, a journey it completes in a mere 8 minutes. This stark contrast highlights the fundamental rule: any particle with mass, from an electron to a human, can only ever approach the speed of light, requiring colossal amounts of energy for even a tiny fraction more speed. But for the massless photon, light speed is not a distant goal. It is its permanent, effortless state of being. Yet even photons are not the only travelers born at near light speed. Deep within the sun's core, another, far more elusive particle is forged in the same nuclear fires. These are neutrinos, subatomic ghosts that pour out of the sun in a constant, unimaginable torrent. Every second, trillions of them pass through your body and through the entire Earth without a single interaction. They are so light that for decades scientists believed they were completely massless, just like photons, and thus should travel at the exact speed of light. This assumption, however, led to one of the greatest mysteries in modern physics, the solar neutrino problem. For years, detectors on Earth carefully counted the neutrinos arriving from the sun, and they consistently found only about a third of the number their models predicted. Where were the missing neutrinos? The answer was not that the Sun was producing fewer, but that the neutrinos themselves were shape-shifters. They oscillate, changing between three distinct types or flavors as they travel through space. This remarkable behavior, confirmed only in the late 1990s, carries a profound implication. For a neutrino to oscillate, it must experience the flow of time, and according to relativity, only particles with mass experience time. Therefore, neutrinos must have a tiny, almost immeasurably small amount of mass. This vanishingly small mass is the reason they travel at almost, but not quite, the speed of light. They are the universe's fastest objects that are not quite perfect, missing the ultimate velocity by a whisper born from a mass so small it redefines the meaning of almost nothing. But even a massless particle's perfect speed is a law of its birth, not a feat of acceleration. To find true cosmic catapults, we must look to objects that are violently flung from rest to impossible velocities. This brings us to the hypervelocity star. Picture an ordinary star similar to our Sun, suddenly torn from its galactic home and hurled into the abyss at over 1 million miles per hour. These are not gentle wanderers, they are celestial cannonballs, and their origin story is one of the most dramatic in the universe. It begins with a binary star system, two stars locked in a graceful orbital dance. Their fatal mistake is wandering too close to the supermassive black hole that lurks at the center of their galaxy. The immense gravity of the black hole violently disrupts their dance. In a cosmic game of gravitational pinball, one of the stars is captured by the black hole, doomed to orbit it forever. Its partner, however, receives a tremendous slingshot effect. It is flung away at such an incredible speed that it achieves escape velocity from the entire galaxy. This is not a gradual acceleration. It is a single, explosive event that propels the star from a stable orbit to an interstellar fugitive in a heartbeat. Once ejected, these stars embark on a lonely, one-way journey. They leave the bright arms of their home galaxy behind, destined to travel forever through the cold, dark emptiness of intergalactic space, solitary beacons racing where few stars will ever shine. These stellar cannonballs are not the only remnants of stellar death racing through the void. The collapse of a massive star can forge an object even denser and far more frantic, a pulsar. When a giant star explodes in a supernova, its core can be crushed under its own immense gravity, collapsing into a city-sized sphere of almost pure neutrons. This neutron star is so unimaginably dense that a single teaspoon of its material would weigh billions of tons on Earth. As this core collapses, it obeys a fundamental law of physics, the conservation of angular momentum. Picture a figure skater pulling her arms in during a spin, causing her rotation to accelerate into a dizzying blur. Now apply that to a star. A star that may have rotated once every few weeks is suddenly shrunk down to a diameter of just a dozen miles. The result is a rotational speed that defies belief. The newborn neutron star spins, and it spins fast. Some of these objects, known as millisecond pulsars, complete well over 700 full rotations every single second. At its equator, the surface of such a star would be moving at a significant fraction of the speed of light. But the true marvel is not just the spin itself, but the lighthouse effect it creates. The pulsar's intense magnetic fields, trillions of times stronger than Earth's, funnel radiation into powerful beams that shoot out from its magnetic poles. If these poles are misaligned with its rotation axis, the beams sweep through space like the beacon of a cosmic lighthouse. When that beam flashes across our line of sight from Earth, we detect a pulse of radiation with every rotation. This creates the iconic metronomic blink that gives pulsars their name. This regularity is not just a curiosity, it is a precision tool. The timing of these pulses is so incredibly stable that millisecond pulsars are among the most accurate clocks in the universe, rivaling and even surpassing the best atomic clocks we have built on Earth. Their steady, rapid heartbeat across the cosmos allows astronomers to use them as navigational beacons for hypothetical interstellar travel and to test the very fabric of spacetime itself. The dizzying spin of a pulsar is only part of the story. To witness true velocity born from desperation, we must peer into the whirlpool of an accretion disk. Picture a star venturing too close to a black hole or a neutron star. The object's immense gravity does not simply pull the star in all at once. Instead, it seizes its outer layers, stretching and tearing the stellar material into a long, thin stream. This stream of superheated gas does not fall straight down. It spirals inward, caught in a frantic orbital dance, forming a vast, flat disk that rotates at a staggering pace. This is the accretion disk, a cosmic hurricane of matter where the rules of motion are pushed to their absolute limit. The material in the outer rim of the disk might orbit at thousands of kilometers per second, but as it gets dragged closer to the central object, it moves faster and faster, compelled by the ever-strengthening gravitational pull. In the innermost regions, just before the final plunge into oblivion, particles can be whipping around at over half the speed of light. This creates a maelstrom of unimaginable violence. The different layers of gas, all orbiting at different speeds, grind against each other with immense friction. This friction generates so much heat that the disk glows with the fury of millions of degrees, emitting not just visible light but powerful X-rays. It is this very process, this frantic spiral into the abyss, that powers some of the most luminous objects in the cosmos. A supermassive black hole feeding on a steady diet of gas can light up its entire galaxy, becoming a quasar so brilliant it can outshine every single star within that island of stars. The light we see from across the universe is not the black hole itself, but the final, furious scream of matter reaching relativistic speeds before it vanishes forever. That final, furious scream of matter is not always a chaotic explosion. Sometimes it is focused into a blade. At the heart of some galaxies, the supermassive black hole does more than just create a glowing accretion disk. It launches two narrow, unimaginably powerful jets of plasma directly from its poles, shooting them out across millions of light years. Most of the time, these jets are pointed off into random directions in space, their full power unseen from our distant vantage point. But when fortune, or perhaps misfortune, aligns one of these jets to point directly at Earth, we see one of the most violent and energetic phenomena in the universe, a blazar. The particles within these jets are not just fast, they are accelerated to over 99.9% the speed of light. This is not a gentle stream, but a focused beam of pure energy, a cosmic firehose of electrons and protons moving at relativistic velocities. The energy required for such an acceleration is almost beyond comprehension, channeled by the black hole's insane rotation and its magnetic fields, which act like the universe's most powerful particle cannon. We detect blazars not by the visible light they emit, but by the torrent of gamma rays and other high-energy radiation that washes over our telescopes. This is the light of matter being torn apart at velocities just a hair's breadth from the cosmic speed limit. To make this spectacle even more bizarre, these jets can appear to move faster than light. This is an optical illusion called superluminal motion. Imagine a jet of plasma moving toward us at nearly the speed of light. The light it emits at a later point in its journey has a shorter distance to travel to reach our eyes than the light it emitted earlier. This compresses the time between the arrival of these light signals, creating the illusion that the jet is moving across the sky at a speed greater than reality allows. It is a cosmic mirage, a trick of relativity and geometry that makes the impossible seem real, all born from a jet of particles racing so fast they break our perception before they break the universe's ultimate law. While the jets of a blazar are a focused beam, the cosmos also fires a relentless, random hail of high-speed projectiles. These are cosmic rays, and they are not rays of light at all. They are mostly single protons, or the nuclei of atoms, stripped of their electrons, hurtling through the vacuum at nearly the speed of light. They are the universe's shrapnel, and they carry energies that are almost incomprehensible. The most energetic cosmic rays ever detected pack a punch equivalent to a major league fastball. Imagine a baseball thrown by a professional pitcher with all its kinetic energy. Now compress that entire explosive force into a single, minuscule subatomic particle smaller than an atom. That is the reality of an ultra-high energy cosmic ray. The mystery is not just their power, but their origin. Where does the universe find a particle accelerator powerful enough to launch a proton with such ferocity? The leading suspects are the same violent engines we have already encountered. The shock waves from supernova explosions can act like massive particle accelerators, boosting protons to these incredible speeds over vast distances. Others might be flung from the chaotic environments around supermassive black holes in active galactic nuclei. Yet, for the very highest energy events, their true source remains one of astrophysics' most enduring puzzles. This invisible rain is constant. Every second, thousands of these particles pierce every square meter of Earth's atmosphere. They are far too energetic to be stopped by our planet's magnetic field. When one of these high-speed invaders slams into a molecule of air high above us, it does not simply bounce off. It shatters it, creating a spectacular cascade. The collision spawns a shower of secondary particles, a downward-pouring fountain of muons, electrons, and photons that rains harmlessly down upon the surface. You are being gently peppered by the debris of these cosmic collisions right now, a silent, invisible reminder of the violent, high-speed universe that surrounds us. This relentless particle rain is a local phenomenon, but the universe holds a far grander, more fundamental kind of motion. Galaxies are flying away from us, and the farther away they are, the faster they seem to be receding. The most distant galaxies we can observe are retreating at velocities that actually exceed the speed of light. This sounds like a direct violation of the cosmic rule we just established, but it is not. The secret lies in a critical distinction. These galaxies are not rocketing through space like a hypervelocity star. Instead, the very fabric of space itself, the stage upon which everything exists, is stretching and expanding. Imagine baking a loaf of raisin bread. As the dough bakes and expands, every single raisin moves away from every other raisin. No raisin is actively traveling through the dough. The space between them is simply growing. This is exactly what is happening to our cosmos. The space between galaxy clusters is continuously stretching. For galaxies that are extremely far apart, the cumulative stretching across that vast distance adds up to a recession velocity greater than light speed. Since nothing is moving through space faster than light, relativity remains perfectly intact. It is the stage itself that is growing, carrying the actors along with it. This incredible expansion is the reason our observable universe has a firm boundary. We can only see the galaxies whose light, traveling at its maximum speed, has had enough time to reach us across the expanding cosmos. Beyond a certain point, the space between us and more distant galaxies is expanding so quickly that their light can never bridge the gap. It is like a swimmer trying to cross a river that is widening faster than they can swim. They will never reach the other side. The light from those ultra-distant realms is forever lost to us, creating a fundamental horizon to our cosmic view. The fabric of space itself can be stretched and squeezed, sending out ripples that travel across the cosmos. These are gravitational waves, a prediction of Einstein's theory of relativity that took a century to confirm. They are not waves of light or sound, but literal distortions in the geometry of spacetime. When a gravitational wave passes through a region, it literally stretches space in one direction while simultaneously squeezing it in the perpendicular direction. This effect is incredibly subtle. A wave powerful enough to be detected from millions of light years away will change the length of a 4-kilometer-long laser beam by less than 1,000th the width of a proton. To measure such an infinitesimal wiggle requires one of the most sensitive experiments ever built, the Laser Interferometer Gravitational Wave Observatory, or LIGO. It works by splitting a laser beam and sending the two halves down long, perpendicular vacuum tunnels. The beams bounce off mirrors and return to recombine. When a gravitational wave passes through Earth, it slightly alters the length of one tunnel relative to the other. One arm gets a little longer while the other gets a little shorter, and then they switch. This minuscule change disrupts the laser light's interference pattern, creating a signal that tells scientists a wave has just passed by. But what cosmic event could possibly create a ripple strong enough to be measured? The answer lies in the most violent mergers imaginable. The first wave ever detected came from two black holes, each with a mass over 25 times that of our Sun, spiraling into each other in a final, frantic dance. In the last fraction of a second before they merged, they whipped around each other at nearly half the speed of light, churning the spacetime around them like a spoon stirring a pot of honey. This colossal disruption sent a powerful ripple racing outward in all directions, a wave that traveled for over 1 billion years at the speed of light before it finally reached Earth and made our detectors tremble. These waves carry energy away at the ultimate speed, the speed of light itself, offering us a completely new way to listen to the symphony of the universe. These violent particle accelerators are not confined to the hearts of distant galaxies. Right here in our own cosmic neighborhood, a smaller yet equally ferocious version of this engine is at work. Meet the microquasar, a stellar mass black hole or neutron star that behaves like a miniature quasar. While its supermassive cousin anchors an entire galaxy, a microquasar is the remnant of a single dead star, typically weighing between 5 and 20 times the mass of our Sun. It often exists in a binary system, siphoning material from a companion star. This stolen gas forms a hot, whirling accretion disk, and just like in its giant relatives, this process can launch two incredibly powerful jets from its poles. The material in these jets is accelerated to over 99% of the speed of light. This means the same fundamental physics that creates a brilliant, galaxy-dominating quasar billions of light years away is also operating on a stellar scale, sometimes just thousands of light years from Earth. One of the most famous examples is a system called SS433, located in our own Milky Way. Its jets are a relentless torrent of plasma, and we can actually watch them change and evolve over time, providing a real-time laboratory to study the mechanics of these cosmic blowtorches. Their proximity allows us to observe details that are lost in the blinding glare of distant quasars, offering a front-row seat to the universal principles of extreme acceleration and relativistic jet formation. This reveals a profound truth. The universe loves to repeat its most dramatic patterns, scaling unfathomable energies down to a size we can almost comprehend. That frame-dragging effect around a microquasar is a mere whisper compared to the roar of its larger cousins. The spin of a black hole is a fundamental property, and some of these cosmic engines rotate at a pace that pushes the very laws of physics to their breaking point. While the event horizon marks a point of no return, the spacetime just outside this boundary is not still. A rotating black hole, described by what physicists call a Kerr solution, does not simply sit in space. It churns the very fabric of reality around it, dragging spacetime along in a swirling, irresistible current. This phenomenon is known as frame dragging. Imagine stirring a cup of coffee. The liquid closest to the spoon is pulled along most strongly, creating a whirlpool. A spinning black hole does the same thing to the empty space around it, forcing space and time itself to rotate. For a black hole spinning at over 99% of its maximum possible rate, this effect becomes so extreme that an object could theoretically enter a region just outside the event horizon, called the ergosphere, and be forced to move faster than light just to remain stationary relative to the distant stars. It is a zone where the universe's rules are stretched to their absolute limit. This frantic rotation is not just a curiosity, it represents a colossal storehouse of energy. The mathematics of general relativity suggest that this rotational energy could, in theory, be extracted. An advanced civilization might fly a spacecraft into the ergosphere, jettison some mass into the black hole, and use the immense kick from the spinning spacetime to be flung back out with more energy than it came in with. This hypothetical process, known as the Penrose process, turns the black hole itself into a galactic power plant, converting its raw spin into usable force. This stored energy is so vast it could outshine entire galaxies of stars, all harnessed from the silent, spinning fury of a dark vortex. Even entire galaxies are not immune to the cosmic speed race. Within the heart of massive galaxy clusters, these great islands of stars are not drifting placidly. They are hurtling through the void at millions of miles per hour, orbiting the cluster's common center of gravity. Our own Milky Way, in a far quieter galactic neighborhood, moves at a more sedate pace. But within a dense cluster like Coma Berenice's, galaxies whip around like bees in a frantic swarm, their velocities driven by the immense collective gravity of thousands of galaxies and a vast ocean of dark matter. This environment is far from serene. The high speeds and crowded conditions lead to a relentless process known as galaxy harassment. When two galaxies pass near each other at these incredible velocities, their gravitational fields interact violently. They do not collide head-on, but their close encounter sends powerful tidal forces surging through each system. These forces can stretch a majestic spiral galaxy, pulling its stars and gas into long, streaming tails, effectively stripping it of its identity and turning it into a bland, elliptical shape over billions of years. Individual stars can be ripped from their galactic moorings entirely, flung out into the cold darkness between galaxies to wander alone. This gravitational turmoil is a constant, high-speed ballet of creation and destruction, proving that even the largest structures in the universe are subject to the relentless physics of motion. We are all cosmic speed travelers, passengers on a celestial vehicle in constant, high-velocity motion. While you sit perfectly still, our entire solar system is racing around the center of the Milky Way galaxy at a breathtaking 514,000 miles per hour. This is not a gentle drift. It is a galactic orbit so vast that a single trip around takes our Sun and its planetary family approximately 230 million years to complete. The last time our solar system was in this particular position, dinosaurs were just beginning their long reign on Earth, yet this orbital journey is only one layer of our motion. The Milky Way galaxy itself, that great spiral of stars we call home, is also on the move. It is being pulled by gravity on a collision course with our nearest large galactic neighbor, the Andromeda Galaxy. Together, we are approaching each other at a combined speed of around 250,000 miles per hour. This means our local trajectory is a complex spiral within a grander fall, a dance of motions that ensures we are never in the same place in the universe twice. From the planet's rotation to its orbit around the Sun, to the Sun's orbit around the galaxy, and the galaxy's own voyage through the cosmos, every single one of us is experiencing a layered, perpetual journey at speeds that defy any earthly sensation. We feel none of this motion, yet it is the unshakable truth of our existence in an expanding, dynamic universe. Our own planet has become a launch pad for its own contenders in the cosmic speed race. The Parker Solar Probe is humanity's boldest attempt to race alongside the Sun's own phenomena. This car-sized spacecraft was not built to travel to the stars, but to dive directly into the sun's outer atmosphere, an environment of brutal radiation and searing heat. Its path to becoming the fastest human-made object ever built is a masterclass in celestial mechanics. The probe does not fight gravity, it uses it. It performs a series of precise flybys of the planet Venus. With each close pass, the planet's gravity acts as a brake, stealing a tiny bit of the probe's orbital energy. This allows the spacecraft to fall deeper into the sun's immense gravity well, like a stone dropping closer and closer to a well's center. With each orbit, its speed increases dramatically. At its closest approach, the Parker Solar Probe will be traveling at over 430,000 miles per hour. That is fast enough to fly from New York to Tokyo in less than 60 seconds. At this incredible velocity, the probe is not just observing the sun from a distance, it is flying through the birthplace of the solar wind, sampling the very particles that race past Earth at millions of miles per hour. This tiny human craft, shielded by a thick carbon composite heat shield, is temporarily joining the ranks of the universe's fastest objects, a testament to our desire not just to watch the cosmic race, but to feel its heat on our own instruments. But what if the universe's ultimate speed limit is not a barrier, but a one-way street? Beyond the realm of observed physics lies a purely hypothetical concept, the tachyon. These are not particles that break the light barrier, they are born beyond it, living their entire existence at speeds faster than light. According to the strange mathematics of theory, such a particle would possess a property known as imaginary mass. This does not mean its mass is make-believe, but that its value is defined by the square root of a negative number, a concept that has no physical counterpart in our slow-moving world. This bizarre property leads to even more mind-bending consequences. For a tachyon, gaining energy would not make it go faster. Instead, adding energy would actually slow it down, pushing it closer and closer to the unattainable speed of light from above. The more you try to power a tachyon, the more sluggish it would become relative to its own impossible standard. Perhaps the most unsettling implication involves time itself. Some solutions to the equation suggest that tachyons would experience time in reverse, traveling backwards through the timeline from our perspective. A tachyon message could arrive at its destination before it was ever sent, creating paradoxes that defy logic. It is crucial to remember that no tachyon has ever been detected. They are a ghost in the machine of theoretical physics, a fascinating tool for exploring the absolute boundaries of our understanding. They force us to ask a profound question. Is the speed of light a universal constant for a reason, a fundamental rule that prevents such temporal chaos from ever unfolding? Sometimes the most profound evidence is found in the wreckage of a cosmic collision. The Bullet Cluster provides a perfect example, a system of two immense galaxy clusters that have violently passed through one another. This event created a natural laboratory on an unimaginable scale, allowing us to witness the separate behaviors of the universe's visible and invisible components. The cluster's countless stars and their galaxies, separated by vast empty tracts, slipped past each other largely unscathed. They are like two swarms of bees that have flown through each other, with only a few distant gravitational nudges altering their path. But the superheated gas that filled the space between those galaxies was not so lucky. This thin, searing plasma is the most normal, visible matter in the cluster. As the clusters collided, this gas experienced a tremendous drag force, like a hand pushing through thick syrup. It was slowed down, compressed, and heated to such extreme temperatures that it now glows intensely in X-rays, marking the site of the impact. What makes this collision truly revolutionary is the map of its total mass. By observing how the cluster's gravity bends the light from more distant galaxies, a technique called gravitational lensing, astronomers could pinpoint where the true mass actually lies. The result was stunning. The majority of the mass, the source of the gravity, did not stay with the slowed-down visible gas. Instead, it traveled right along with the seemingly empty regions populated by the galaxies. This was direct, observational proof of dark matter. The collision literally stripped the normal matter away from the invisible gravitational scaffolding, revealing that the true skeleton of our cosmos is built from something we cannot see, a ghostly substance that dictates the motion of galaxies while remaining forever in the shadows. The death of a star is a violent rebirth that echoes across light years. When a massive star, many times heavier than our Sun, finally exhausts its nuclear fuel, its own immense weight becomes its executioner. The outward pressure from fusion vanishes, and the star's core collapses under its own gravity in less than a single second. This collapse does not happen gently. The core, an iron sphere about the size of Earth, crushes down into a city-sized ball of neutrons. The inrushing outer layers of the star hit this newly formed, incredibly dense neutron core and rebound with unimaginable force. This rebound creates a titanic shockwave, a spherical blast of energy that races back out through the star's body. This shockwave begins its journey at an incredible speed, a significant fraction of the speed of light, moving at tens of thousands of kilometers per second. It is a supersonic bulldozer of pure force, tearing the star apart from the inside out. The entire star does not just fade away, it is detonated, its outer layers violently ejected into space in one of the most energetic events since the Big Bang itself. This cataclysmic explosion is the very furnace where the universe forges the elements of life. During its stable life, a star produces elements like carbon and oxygen through nuclear fusion. But it is only in the heart of this supernova inferno, within the unimaginable temperatures and pressures of the expanding shockwave, that even heavier elements are created. Atoms of gold, silver, and uranium are forged in this single, spectacular blast. The shockwave then acts as a cosmic delivery service, hurling these newly minted elements far and wide, scattering them across interstellar space. Every atom of iron in your blood, every speck of calcium in your bones, and every piece of gold in a wedding ring was once forged in the heart of a dying star, and then catapulted across the galaxy by a shockwave moving at a fraction of light speed. We are all, quite literally, the children of stellar explosions. While we track the steady spin of pulsars and the long voyages of stars, the cosmos also sends us messages that are over in a flash. Fast radio bursts are among the most fleeting and powerful signals we have ever detected. These are not gentle whispers from space. They are colossal blasts of radio wave energy, brighter than entire galaxies, yet they last for only a few thousandths of a second. In that brief blink, a single fast radio burst can release more energy than our Sun puts out over 3 entire days. The brevity of these events is their most important clue. Because information cannot travel faster than light, an object cannot appear to change faster than the time it takes light to cross it. A flash that lasts only 1 millisecond must come from a source no larger than the distance light can travel in that sliver of time, which is about 300 kilometers. This forces the source to be incredibly small and dense, likely a compact object no bigger than a city. The leading suspect for many of these bursts is a type of neutron star with an unimaginably powerful magnetic field, a magnetar. The magnetic field around a magnetar is so intense that it can literally twist the star's crust. Imagine the entire surface of a sun-sized object, but with the density of an atomic nucleus being wrung like a dish rag. This buildup of stress can lead to a catastrophic starquake, a seismic event that cracks the neutron star's surface and unleashes a firestorm of radiation in a fraction of a millisecond. Other bursts might be produced in the final, frantic moments before 2 neutron stars spiral into each other and merge. These signals arrive without warning, a flash of cosmic noise from an unimaginably powerful engine in a distant galaxy, leaving behind a mystery that vanishes almost as soon as it appears. These brilliant hotspots are not what they seem. Within the blazing jets of distant quasars, astronomers sometimes pinpoint intensely bright regions where the high-speed jet slams into a slower-moving cloud of intergalactic gas. These collisions create a brilliant flare, a cosmic roadblock that glows with immense power. Logic would suggest we could simply clock the speed of this hotspot as it moves along the jet's path, but the measurements yield an impossible result. Some of these flares appear to race across the sky at speeds up to 10 times faster than light. This superluminal motion is a profound illusion, a cosmic magic trick played by the sheer velocity of the jet and the finite speed of light itself. Picture a single searchlight on a dark night, sweeping its beam across a distant bank of clouds. The bright patch of light on the clouds can easily travel faster than light, racing across the landscape in an instant, even though the searchlight itself is moving quite slowly. The hotspot in a quasar jet is similar. The jet is a continuous flow of plasma moving at over 99.9% of light speed. As it flows, it encounters obstacles and creates new bright regions. The material causing the flare is not a single object moving laterally, but a wave of energy propagating along the jet's path. Because the jet is pointed almost directly towards us, the light from a newer flare near the base of the jet has a much shorter distance to travel to reach us than the light from an older flare further out. Our telescopes see the newer flare brighten first, and then the older one, compressing the time between these two events in our observations. This makes the apparent motion across the sky seem impossibly fast, a geometric sleight of hand that makes the real, already staggering speed of the jet appear to shatter the universe's ultimate law. Racing through the galactic halo at hundreds of kilometers per second are immense, silent rivers of gas. These are the high-velocity clouds, colossal structures of mostly hydrogen that dwarf entire star systems, yet they drift unseen against the backdrop of the Milky Way. Their name comes from a single, puzzling observation. Their motion does not sync with the graceful rotation of our galaxy's spiral arms. While most of the galaxy's gas and stars orbit the center in a relatively orderly disk, these clouds are moving on wildly different, often inclined paths. Some are caught in a long, slow fall, pulled inexorably toward the galactic disk by gravity. Others are barreling through at bizarre angles or even speeding away, suggesting a far more violent origin. This high-speed gas is not merely passing through. It is the very lifeblood of future stars, a reservoir of raw material falling in from the vast emptiness between galaxies. These clouds are the cosmic rain that will one day condense into new suns and solar systems, a continuous, high-speed accretion that fuels the galaxy's ongoing evolution. But the clouds moving on the most extreme trajectories tell a darker story. They are likely the ghostly remains of tiny dwarf galaxies that ventured too close to the Milky Way. Our galaxy's immense gravity stretched these small satellite systems into long, streaming filaments of stars and gas, a process of tidal disruption that tore them apart over billions of years. The high-velocity clouds are the final, fading echoes of those ancient collisions, the last gaseous screams of galaxies cannibalized by our own. This reveals our galaxy not as a static island, but as a dynamic, ever-changing ecosystem, one that grows by capturing and consuming smaller neighbors at breathtaking speeds. The crust of a magnetar is a prison of unimaginable forces. This neutron star's magnetic field is so powerful it could erase the data on every credit card on Earth from halfway to the moon. Under that immense strain, the star's solid crust, a lattice of iron nuclei, builds up titanic stress until it can no longer hold. It cracks. This event is a starquake, and while the physical shift in the crust might be only a few centimeters, the consequences are cosmic. The sudden fracture sends a powerful shockwave racing not through rock but through the star's own magnetic field. These are Elfvane waves, magnetic disturbances that propagate along the field lines. In the magnetar's impossibly dense and magnetized environment, these waves do not travel slowly. They surge outward at a significant fraction of the speed of light, rapidly reorganizing the entire magnetic field structure in an instant. This violent reconfiguration unleashes a firestorm. The twisted magnetic field lines snap and reconnect, accelerating electrons to near light speeds and forcing them to spiral in intense bursts of radiation. The result is a flare of gamma rays and X-rays so brilliant it can temporarily outshine every other source in the galaxy combined. For a fleeting moment, this tiny, city-sized object becomes the brightest thing in the Milky Way, its cry of magnetic agony echoing across thousands of light years. Even the darkest objects in the cosmos are not immune to the laws of motion. When two black holes spiral inward for their final, cataclysmic merger, the event is not perfectly symmetrical. As they whip around each other at nearly the speed of light, they emit gravitational waves, ripples in spacetime that carry away not just energy but momentum. Think of it like firing a rocket engine in one direction. The craft recoils in the opposite direction. In the final moments of a black hole merger, the last, most powerful burst of gravitational waves acts as that rocket engine. If this final burst is stronger in one particular direction, due to the spin and alignment of the two black holes, the newborn black hole recoils violently in the opposite direction. This is the black hole kick, a gravitational slingshot of unimaginable power. The resulting single black hole, an object with a mass dozens of times greater than our Sun, can be ejected from its home at speeds exceeding 5,000 kilometers per second. That is fast enough to cross the entire United States in less than a single second. This creates a rogue black hole, a dark predator cast out from its galactic core. It leaves behind the bright lights of its home galaxy, doomed to wander the vast, empty tracts of intergalactic space. With no stars to feed on and no accretion disk to glow, it becomes an invisible traveler, its presence detectable only by the subtle gravitational wobble it imparts on the faint light of distant background stars. How many of these dark, high-speed ghosts are silently racing through the void, completely unseen from our vantage point? This relentless wind originates from the Sun's own atmosphere, a perpetual gale of charged particles that defines the very bubble of our solar system. The solar wind is not a single, uniform breeze, but a variable and dynamic flow with two distinct personalities. The slow solar wind is a dense, meandering river, traveling at a relatively placid 300 to 400 kilometers per second. It emerges from the Sun's more complex, magnetically active regions near its equator. The fast solar wind, however, is a different beast entirely. It is a thinner, far more rapid stream, racing away from the Sun at a blistering 500 to 800 kilometers per second. Its birthplace is the coronal hole, a vast, dark region in the Sun's outer atmosphere where the magnetic field opens up directly into space. In these areas, the Sun's grip is weaker, allowing the superheated plasma to escape more freely and accelerate to incredible speeds, like water shooting from a high-pressure hose with no nozzle to restrict it. This constant, high-speed outflow carves out a vast protective bubble in interstellar space known as the heliosphere. This is the Sun's sovereign territory, a zone where the solar wind dominates, shielding our entire planetary system from the harsh galactic cosmic rays that permeate the void beyond. When these charged particles, traveling at millions of miles per hour, finally encounter Earth's magnetic field, they are funneled toward the poles. There, they collide with atoms in our upper atmosphere, imparting their immense kinetic energy and causing the air itself to glow. This is the majestic dance of the orrery, a direct and beautiful consequence of our star's high-speed, invisible breath. While our galaxy whirls with cosmic speed demons, the fastest moving star you can actually see in the night sky is a quiet red dwarf known as Barnard's star. It holds a unique title, the greatest proper motion of any star in our heavens. Proper motion is the star's apparent drift across the celestial sphere, the tiny shift in its position relative to the more distant, seemingly fixed background stars. Every year, Barnard's star moves a measurable 10.3 arcseconds. To visualize that, an arcsecond is an incredibly small angle, about the size of a dime seen from 2 miles away. This annual crawl seems insignificant, but over a human lifetime, its movement becomes clear. In just 180 years, it will have shifted a distance equal to the width of the full moon. This remarkable apparent speed is a product of 2 factors working together. First, Barnard's star is one of our closest neighbors, a mere 6 light-years away. Second, it possesses a genuine high velocity relative to our Sun, a sideways or tangential speed of about 90 kilometers per second. This combination makes it a standout sprinter in our celestial backyard. Its rapid drift is a powerful reminder that speed in the cosmos is deeply tied to our own vantage point. A distant hypervelocity star, blazing through the void at millions of miles per hour, might appear virtually motionless to us because of its immense distance. Meanwhile, Barnard's star, moving at a more modest pace, puts on a visible show simply because it is passing so close by. It is a lesson in cosmic perspective, where a nearby jogger can seem to outpace a faraway race car, all based on the geometry of our view from Earth. Our local cosmic journey is far more complex than a simple orbit around the galactic center. The entire Milky Way, along with the dozens of other galaxies in our local group, is caught in a far grander river of motion, all flowing toward a mysterious and hidden destination. This colossal current carries us at over 600 kilometers per second toward a specific point in the constellation Centaurus, a region astronomers call the Great Attractor. This is not a motion against the universe's expansion, but a local current superimposed upon it, a vast, slow drift of countless galaxies pulled by a gravitational anchor we cannot directly see. The Great Attractor is not a single, brilliant object. Its center is obscured by the dusty disk of our own Milky Way, hidden behind a cosmic veil we call the Zone of Avoidance. For decades, this region was a blind spot in our maps of the sky. What we know comes from observing the motion of thousands of galaxies around us, all revealing this consistent, unsettling drift toward a single point. The sheer mass required to pull our entire galaxy and its neighbors is staggering, equivalent to tens of thousands of Milky Ways. This gravitational behemoth is likely the core of the Laniakea supercluster, a filamentary web of over 100,000 galaxies to which we belong. The true source of this immense pull is not the visible galaxies themselves, but the unfathomable concentrations of dark matter that form the supercluster's skeleton. We are like leaves floating on a slow, wide river, finally sensing the powerful pull of a distant waterfall we have not yet seen, drawn forward by the invisible hand of gravity on the grandest possible scale. Those stellar explosions are mere firecrackers compared to the universe's ultimate detonations. Gamma-ray bursts are the most powerful explosions known to exist, capable of outshining entire galaxies for a few fleeting seconds. In that brief moment, they release more energy than our Sun will emit over its entire 10-billion-year lifetime. The key to this staggering power lies not just in the energy itself, but in its blistering, focused speed. The most common type, long-duration gamma-ray bursts, are thought to be the birth cries of black holes, created when the core of a rapidly spinning, massive star collapses directly into a singularity. This is not a gentle supernova, but a hypernova, an event of almost unimaginable violence. Instead of exploding in all directions, the dying star channels its fury into 2 narrow jets like cosmic blowtorches that erupt from its poles. The material within these jets is not simply fast, it is accelerated to an almost perfect velocity, 99.999% of the speed of light. To understand what this truly means, we must turn to a concept from relativity known as the Lorentz factor. This is a measure of how severely time and space warp at such immense speeds. For a jet moving this fast, the Lorentz factor is enormous, around 1,000. This means that from our perspective, watching from a safe distance, time within the jet itself is slowed down by a factor of 1,000. Imagine a clock riding along with the jet's material. For every 1 second that passes on that clock, 1,000 seconds pass for us here on Earth. This incredible time dilation compresses the entire energy release from the jet's perspective. What might feel like a leisurely, several-hour-long energy release to an observer within the jet is squeezed into a pulse of gamma rays that lasts only a few seconds from our distant vantage point. All that catastrophic power, the light of millions of suns, is focused and concentrated into the brief flash we detect, a flash born from matter racing so close to the cosmic speed limit that time itself nearly grinds to a halt. But even a single pulsar spin pales before the dance of a cosmic duo. In the constellation Aquila, a pair of neutron stars known as the Hulse-Taylor binary pulsar perform a frantic orbital waltz. These two incredibly dense city-sized objects are locked in a gravitational embrace, orbiting their common center of mass at speeds reaching 300 kilometers per second. That is 1,000 times faster than a jet fighter, a velocity so immense it creates effects predicted by Einstein but never before seen so clearly. The intense gravity and high speed of this system cause the orbits themselves to slowly rotate, a phenomenon called the precession of the periastron. The point where the two stars pass closest to each other gradually shifts over time, tracing a rosette pattern in space rather than a simple, repeating ellipse. This is a direct consequence of spacetime being warped by the star's immense masses, a subtle confirmation of general relativity in action. Yet the most profound discovery from this system was not the dance itself, but its slow, inevitable decay. The two pulsars are gradually spiraling inward, losing orbital energy. The only way this energy could be carried away is through ripples in the fabric of spacetime itself, gravitational waves. The Hulse-Taylor pulsar provided the first indirect but undeniable proof that these waves are real, that the universe truly does ripple and bend with the motion of massive objects. This monumental discovery, which earned its discoverers the Nobel Prize in Physics, opened an entirely new window onto the cosmos, transforming our ability to listen to the universe's most violent events and proving that even the most subtle cosmic motions can reveal the deepest truths. The frantic dance of galaxies within a cluster is governed by a profound cosmic balance. This is the virial theorem, a fundamental law of physics that links motion to gravity. In any stable, gravitationally bound system, from a tiny solar system to a vast cluster of galaxies, the total kinetic energy of all the moving objects is intimately tied to their total potential energy. Think of it as a cosmic tug of war. The kinetic energy is the desire of every galaxy to fly apart, while the potential energy, the gravity, is the force holding them all together. For the cluster to remain stable over billions of years, these two opposing energies must exist in a very specific, balanced ratio. This gives astronomers a powerful scale. By measuring how fast the individual galaxies are whizzing around inside a cluster, we can directly calculate the total mass, the collective gravity, that must be present to keep them from flying off into the void. When scientists first applied this theorem to great clusters like Coma Berenices, they got a shocking result. The speeds of the galaxies were far, far too high. The visible matter, the combined light of all the stars in all those galaxies, could not possibly generate enough gravity to hold such speedy objects in check. According to the simple math of the virial theorem, these clusters should have torn themselves apart long ago. The only possible explanation was that there had to be an immense amount of invisible mass, a hidden gravitational anchor providing the extra pull. This was one of the earliest and most compelling lines of evidence for dark matter, revealing that what we see in the cosmos is merely the glitter on the surface of a vast, unseen ocean. The gravitational grip of a neutron star is a prison from which almost nothing can escape. To break free from its surface, an object would need to achieve a velocity of around 100,000 kilometers per second, a significant fraction of the speed of light. This is the neutron star's escape velocity, the minimum speed required to overcome its immense gravitational pull and soar away into space. To put this into perspective, Earth's own escape velocity is a mere 11 kilometers per second, a leisurely stroll compared to the neutron star's cosmic sprint. The reason for this staggering difference lies entirely in the neutron star's unbelievable density. All that remains of a giant star's core has been crushed into a sphere only about 20 kilometers across. This means you are starting your escape attempt from a point incredibly close to an almost unimaginable concentration of mass, a gravitational well so deep that climbing out demands a truly relativistic speed. The consequences of this gravity are both violent and counterintuitive. Imagine something as gentle and light as a marshmallow falling toward a neutron star. As it plummets, it would accelerate, gaining immense kinetic energy from the star's gravitational field. By the time it impacted the solid surface, that single marshmallow would strike with the energy of a hydrogen bomb. This is not because the marshmallow itself is powerful, but because the neutron star's gravity has done the work, accelerating a tiny mass to such an incredible velocity that its energy becomes apocalyptic. This is the raw, transformative power of gravity when matter is compressed to its absolute limit, turning a simple fall into a cataclysmic event. Our own solar system holds a quiet, century-old mystery that only the speed of a planet could solve. For generations, astronomers tracked the orbit of Mercury, the swiftest planet in our solar system. They noticed a subtle, persistent drift in its path. The entire elliptical orbit was slowly rotating around the Sun, a phenomenon called precession. Newton's laws of gravity could explain most of this drift caused by the gentle gravitational tugs from the other planets. But a tiny portion of the shift remained stubbornly unaccounted for, a minuscule wobble that math alone could not solve. This tiny anomaly was a splinter in the mind of classical physics. Then came Albert Einstein with his revolutionary theory of general relativity. He proposed that Mercury's incredible orbital velocity, a blistering 47 kilometers per second as it sweeps close to the Sun, was the key. This speed, combined with the Sun's powerful gravity, meant Mercury was moving through a region where spacetime itself was significantly warped. The planet was not simply being pulled by a force, it was following a curved path in a distorted geometry. Einstein's equations showed that this warping would cause the planet's point of closest approach to the Sun to gradually shift forward over time. When he calculated the exact amount, the result matched the observed anomaly perfectly. That tiny, unexplained wobble in Mercury's orbit became one of the first and most powerful validations of general relativity, proving that even the motion of a single, fast-moving world could reveal the deepest nature of space and time. Even the most isolated supernova is not alone in its work. Across the spiral arms of a galaxy, vast stellar nurseries give birth to thousands of stars at once. Many of these newborn stars are massive, luminous, and destined for short, violent lives. Their collective fury does not just light up the neighborhood, it carves it. The combined effect of their powerful stellar winds and their eventual, sequential supernova explosions creates a phenomenon far grander than any single blast, a superbubble. Imagine a single soap bubble blown by a child. Now, imagine a dozen children blowing through the same wand at once. The result is a colossal, expanding sphere of hot gas that pushes outward with relentless force. Inside a star-forming region, this is exactly what happens. Dozens of supernovae exploding over millions of years, along with the constant, high-pressure gale from the most massive stars, inject an unimaginable amount of energy into the surrounding space. This energy heats the interstellar gas to millions of degrees, creating a vast, low-density cavity that expands outwards, its shock front plowing into the colder, denser galactic medium at speeds of dozens of kilometers per second. This is not a gentle inflation. It is a galactic excavation project, a cosmic bulldozer clearing out immense volumes of space. The walls of these superbubbles are where the true magic happens. As the expanding shockwave rams into surrounding clouds of cold hydrogen gas, it compresses them. This compression is the universal trigger for star birth. The gas clouds, squeezed beyond their ability to remain stable, begin to fragment and collapse under their own gravity, igniting a new generation of stars. This creates a self-perpetuating cycle. One generation of massive stars dies in a series of blasts that clears a cavity and triggers the birth of the next generation, often right on the bubble's edge. We see the evidence of these structures across our own Milky Way, immense chimneys and shells that rise thousands of light-years above the galactic plane, their relentless expansion constantly reshaping the very architecture of our galaxy. These violent stellar births are not just about pulling material in, they are also about throwing it out with incredible force. Deep within a collapsing cloud of gas and dust, as a newborn protostar greedily feeds from its surrounding disk, it also unleashes a paradox. Twin beams of gas erupt from its poles, shooting away at speeds of hundreds of kilometers per second. This is a protostellar outflow, a star's first defiant cry against the gravity that formed it. The exact engine behind these jets is a marvel of cosmic mechanics, likely powered by the star's intense magnetic fields and the frantic spin of its accretion disk. The material is not simply blown away, it is focused and collimated into narrow, searingly hot beams that can stretch for light years across the nebula. These jets are far more than just exhaust, they are essential to the star's very formation. By carrying away excess energy and angular momentum, they allow the fledgling star to continue accreting mass without spinning itself apart. The true spectacle, however, happens where these high-speed jets slam into the slower-moving gas of the interstellar cloud. The collision is so violent it shocks the gas, heating it to the point where it glows with an ethereal, often knotty light. Astronomers call these brilliant collisions Herbig-Haro objects. They are not the stars themselves, but the luminous splash zones created by the star's energetic outflows, acting as temporary but brilliant signposts that mark the location of a stellar nursery. These objects are dynamic and can change over just a few years as new clumps of jet material ram into older ones, creating a visible record of the star's fiery, high-speed infancy. Our journey toward the Great Attractor is just one leg of a far grander voyage. The entire local group, a collection of dozens of galaxies including our own, is caught in a river of motion that spans hundreds of millions of light years. This immense flow carries us not only toward the obscured mass of the Great Attractor, but beyond it toward a truly colossal destination, the Shapley supercluster. This structure is the single most massive concentration of matter we have identified in our observable cosmic neighborhood, a staggering gravitational anchor pulling on everything around it. This reveals a profound hierarchy in the universe's architecture. Galaxies group into clusters, clusters bind into superclusters, and these superclusters themselves are arranged in vast filaments and walls, forming a cosmic web of unimaginable scale. Our motion toward Shapley is the ultimate expression of gravity's relentless, long-range pull. It is a slow, patient current that has been guiding the trajectories of countless galaxies for billions of years, a silent river flowing through the expanding void. This grand drift puts our place in the cosmos into a humbling perspective. We are not merely orbiting the galactic center, we are passengers on a galaxy that is itself a passenger in a cluster, all flowing together in a supercluster, moving toward the greatest local concentration of mass in the universe. How many more of these immense currents and attractors lie beyond the horizon of our observation, silently shaping the paths of islands of stars we cannot even see? The eerie blue glow of the Crab Nebula is a ghost story told by electrons moving at impossible speeds. This is not the gentle light of a star, but something far more violent and beautiful, a phenomenon known as synchrotron radiation. It is the direct, visible signature of matter being pushed to the absolute brink of light speed. The story begins when electrons are caught in an invisible cosmic trap, a powerful magnetic field. If these electrons are then accelerated to over 99% of the speed of light, as they are in the shock waves around pulsars or within the jets of active galaxies, they cannot travel in a straight line. The magnetic field forces them into a frantic, spiraling path, corkscrewing around the invisible field lines. This relentless, high-speed change in direction, this violent acceleration, forces the electrons to shed energy. They radiate it away as a brilliant, broad spectrum of light, from radio waves all the way up to X-rays and gamma rays. The Crab Nebula, the expanding wreckage of a supernova witnessed on Earth in 1054, is powered by this very process. At its heart spins a pulsar, a neutron star rotating 30 times every second. This frantic spin generates a furious wind of relativistic electrons and a powerful magnetic field. When this wind slams into the slower-moving nebula gas, it creates a shock wave that accelerates the electrons to near light speed, causing the entire cloud to glow with that distinctive, ethereal synchrotron light. We are not just seeing a cloud of gas, we are witnessing the afterimage of a high-speed dance, a cosmic light show powered by particles on the very edge of reality. The fastest a human being has ever traveled was inside the Apollo 10 command module, hurtling back from the moon at nearly 40,000 kilometers per hour. That velocity feels almost godlike from our earthly perspective, a testament to human ingenuity and courage. Yet when we place it beside the cosmic speeds we have been exploring, it becomes a sobering reality check. That 40,000 kilometers per hour translates to just about 11 kilometers every single second. Compare that to the lonely hypervelocity star ejected from its galaxy at over 1 million miles per hour, or the Parker Solar Probe, our own robotic creation, diving toward the Sun at more than 430,000 miles per hour. Even our fastest terrestrial machines are left in the cosmic dust. The fastest car ever built, a rocket-powered vehicle, managed to break the sound barrier and reach about 1,228 kilometers per hour. For a breathtaking moment, that was the pinnacle of human speed on the ground. But that immense effort, that roar of power and engineering, barely registers as a crawl next to the silent, effortless drift of Barnard's star across our sky. These comparisons are not meant to diminish our achievements, but to frame them within the true, mind-bending scale of the universe. They highlight a profound gap between the velocities we can engineer and the natural, relativistic speeds that are commonplace out there, reminding us that the cosmos operates on a playing field we are only just beginning to comprehend. That grand drift toward the Great Attractor is just a local ripple on the surface of a far more profound cosmic current. This universal motion is governed by a simple, yet revolutionary, principle known as the Hubble-Lemaître law. It states a breathtakingly direct relationship. The farther away a galaxy is from us, the faster it appears to be racing away. This is not a coincidence. It is the primary echo of the universe's violent birth. The connection is captured in a deceptively simple formula: velocity equals Hubble's constant multiplied by distance. Hubble's constant is the key number, the rate at which the universe is expanding today. For a galaxy 100 million light-years away, we plug that distance into the equation and find it is receding from us at approximately 2,200 kilometers per second. That is fast enough to cross the entire Atlantic Ocean in less than a single heartbeat. A galaxy twice as far away at 200 million light-years is not just receding faster, it is moving away at twice that speed, around 4,400 kilometers per second. This beautifully linear relationship is exactly what you would expect if you were watching the aftermath of a colossal explosion, with every piece of shrapnel flying outward from a common center. We are not at the center of this expansion, of course. From the perspective of any other galaxy, every other galaxy would also appear to be fleeing, with the most distant ones moving the fastest. This uniform, accelerating flight is the most compelling evidence we have for the Big Bang. the moment when all of space, time, and matter erupted into being, setting every galaxy adrift on a stretching fabric that continues to widen even now. Deep within the heart of a neutron star, sound itself is transformed by the crushing density. The speed at which a pressure wave travels through a material defines its sound speed, and on Earth, this is a leisurely few kilometers per second. But the crust of a neutron star is no ordinary solid. It is a perfect, rigid lattice of atomic nuclei, packed so tightly by gravity that the space between them has been virtually eliminated. In this environment, the speed of sound is no longer a gentle ripple. It soars to a significant fraction of light speed, potentially reaching over half the ultimate velocity. This is not about something you could hear, but about the lightning-fast communication of force. When a starquake cracks this crust, the shockwave does not travel like an earthquake through rock. It propagates almost instantaneously, a near-light-speed jolt that realigns the entire star's rigid surface in a heartbeat. This incredible speed is vital for explaining the sudden glitches astronomers observe in pulsars. A glitch is a tiny, sudden increase in a pulsar's spin rate. One leading theory suggests that a starquake deep within the crust causes a momentary change in the star's shape, making it slightly more compact. Just as a spinning ice skater pulls her arms in to spin faster, the neutron star's rapid contraction causes its rotation to suddenly speed up. For this to happen across the entire star at once, the change in pressure must be communicated faster than the star is rotating. With sound traveling at relativistic velocities, the entire crust can adjust in unison, creating the precise, instantaneous glitch we detect from light years away. The sound speed in this exotic material is not just a number, it is the clockwork mechanism that allows a city-sized star to hiccup and then resume its metronomic pulse across the cosmos. Our solar system's journey around the galactic center marks time on a scale almost beyond human comprehension. This immense orbit defines what astronomers call a galactic year, a single revolution of the Sun around the Milky Way that lasts between 225 and 250 million Earth years. This is not merely a distance traveled, it is the universe's grandest timepiece. The last time our solar system was in this precise position within the galaxy, the Triassic period was just beginning. The supercontinent of Pangaea was intact, and the first small dinosaurs were emerging to begin their long reign over the planet. In the entire history of complex life on Earth, our world has completed only about 20 of these galactic orbits. Every major epoch, from the age of dinosaurs to the rise of mammals and the dawn of humanity, fits within a tiny slice of this cosmic cycle. This framing transforms our sun's velocity from a simple number into the second hand on a celestial clock, ticking off chapters in the story of life itself. Our planet's motion is embedded within this grand spiral dance, a slow, patient waltz that has continued for billions of years, carrying all of us through the galactic seasons. A star's final detonation is rarely a perfect sphere. When the core of a massive star collapses, the ensuing supernova explosion can be a lopsided, chaotic event. This asymmetry is the engine behind a natal kick, a cosmic recoil that violently shoves the newborn stellar remnant. The physics behind this kick are born from a fundamental imbalance. If more neutrinos or explosive debris are blasted out in one direction during the collapse, the conservation of momentum demands an equal and opposite reaction. The fledgling neutron star or black hole recoils in the opposite direction, like a cannon firing from a ship. This is not a gentle nudge. The remnant can be launched at speeds exceeding 500 kilometers per second, fast enough to cross the entire United States in under 10 seconds. This immense velocity explains a long-standing mystery. Many of the pulsars we detect are not peacefully drifting within the crowded galactic disk where stars are born. Instead, they are high above or below that plane, solitary travelers on one-way trips into the galactic halo. These are runaway stellar corpses, their high-speed flight a direct result of that violent, off-center birth kick. They leave behind the glowing nebula of their own destruction, racing into the darkness as silent, spinning tombstones for the stars they once were. Beyond the last whispers of the solar wind, in a region of near-total darkness, lies the solar system's final frontier. The Oort cloud is a vast, spherical shell of icy remnants, a cosmic deep freeze stretching nearly halfway to the next star. Its trillions of frozen objects are so far from the sun that our star appears as little more than a particularly bright point of light, its gravitational grip reduced to the faintest of whispers. This tenuous hold makes the Oort cloud a place of constant, subtle turmoil. The gentle but relentless tidal pull of the Milky Way's collective gravity, combined with the occasional close passage of another star, acts like a perpetual cosmic nudge on these dormant worlds. A slight gravitational tug from a star passing light years away is enough to upset a fragile orbital balance that has held for eons. When this happens, an icy planetesimal is shaken from its slumber. It begins a long fall inward, accelerating steadily as the sun's gravity grows stronger. What starts as a barely perceptible drift transforms into a breathtaking plunge. By the time this object, now a long-period comet, reaches the inner solar system, it is moving at tremendous speeds relative to the planets, a silent iceberg racing through the void on an orbit that may take millions of years to complete. These comets are the messengers from our system's outermost edge, their high velocity a direct result of a fall from an almost unimaginable height, a journey begun by the gentlest of pushes from the galaxy itself. Magnetic fields give the void a voice, and their whispers travel at a specific critical velocity. This is the Alfvén speed, the precise rate at which a magnetic disturbance ripples through a sea of charged particles, a plasma. Most of the visible matter in the universe exists not as solid objects, but as this fourth state of matter, a gas so hot that electrons have been stripped from their atoms, leaving them free to conduct electricity and interact with magnetic fields. In the vast, near-perfect vacuum between the stars, this interstellar plasma is incredibly thin, yet it is laced with these invisible magnetic fields. The Alfvén speed is the fundamental rhythm of this magnetized ocean. It determines how energy propagates, how shockwaves from supernova behave, and even how the solar wind interacts with the galaxy's own magnetic field. In the quiet stretches of interstellar space, this critical speed might be a modest few tens of kilometers per second. But within the chaotic aftermath of a stellar explosion or near a powerful pulsar, it can surge into the hundreds of kilometers per second. This single number acts as a cosmic dividing line. When a cloud of gas or a shockwave moves slower than the Alfvén speed, the magnetic field can easily adjust, bending and flexing to accommodate the motion. But when something tries to plow through the plasma faster than this magnetic sound speed, the field can no longer smoothly ripple out of the way. It stiffens, creating a sharp, abrupt boundary, a shock front. It is at these magnetic walls where the flow abruptly transitions from sub-Alfvénic to super-Alfvénic that the universe finds one of its most efficient particle accelerators. Chaotic magnetic fields at these shock fronts can trap charged particles, forcing them to cross the boundary again and again, each time gaining a little more speed until they are flung away as the high-energy cosmic rays that constantly rain down upon us. That sideways drift of Andromeda is a subtle but crucial part of our cosmic future. While our two galaxies are rushing toward each other for a dramatic collision, Andromeda is not falling straight in. It is also sliding sideways relative to our position, a motion astronomers call its proper motion. This tangential velocity is a modest 50 to 100 kilometers per second, a tiny fraction of its head-on approach. Yet this gentle sideways slide is what will transform a catastrophic head-on crash into a long, graceful dance. Without it, the Milky Way and Andromeda would plunge directly into one another, a single, violent merger. Instead, that sideways momentum will cause the two galaxies to first sweep past each other, like two vast ships passing in the night. Their mutual gravity will then pull them back together, leading to a second, closer pass. This gravitational tango will repeat over billions of years, each loop drawing them tighter, slowly merging their stars and gas into a single, new galaxy. This three-dimensional understanding of our motion is essential. It is the difference between predicting a car crash and forecasting a complex orbital ballet. The first close encounter is still set for about 4 billion years from now, but thanks to that tiny sideways velocity, the final merger into a giant elliptical galaxy will be a far more gradual and majestic process, a cosmic waltz set to the slowest music imaginable. A comet's journey is a breathtaking plunge from frozen silence into a roaring furnace. These ancient icebergs spend most of their lives drifting in the outer darkness of the solar system, but when their elongated orbits finally curve inward, they begin a spectacular transformation. Drawn by the sun's gravity, a comet falls faster and faster, building speed like a stone dropped from a skyscraper. By the time it reaches its closest point to the sun, a moment called perihelion, it can be racing along at well over 100 kilometers per second. That is more than 20 times faster than a bullet, a velocity so immense it defies any earthly experience. This blistering speed is only half the spectacle, for it arrives hand in hand with brutal heat. The comet's nucleus, a dusty ball of frozen gases and water ice, is suddenly blasted by solar radiation. The ices do not melt, they instantly turn from solid to gas in a process called sublimation, erupting in a glorious geyser of vapor and dust. The sun's radiation pressure and its own solar wind then blow this material away, sculpting it into the comet's iconic twin tails. One tail, a glowing stream of ionized gas, always points directly away from the sun, pushed by the solar wind. The other, a broader, curving dust tail, follows the comet's orbital path. This magnificent display is not a sign of the comet's death, but of its desperate survival. The same incredible speed that creates the tail also saves the comet, allowing it to whip around the sun in a matter of hours before its momentum carries it back out into the freezing void, a brilliant but temporary visitor from the solar system's deepest cold. This brilliant illusion is a direct signature of matter racing at the ultimate edge of possibility. When the high-speed jet of a blazar is aimed almost directly at Earth, the light we receive is not just bright, it is fundamentally transformed by its velocity. This phenomenon is called relativistic beaming, and it warps our perception of reality. The particles within the jet, moving at over 99.9% of light speed, are firing their photons toward us like a high-speed train emitting flashes of light. From our perspective, these light waves are not just arriving quickly, they are being compressed. The motion of the jet toward us squeezes the wavelengths of the light, shifting them toward the blue end of the spectrum. More importantly, the light's energy is dramatically concentrated. The photons are not emitted evenly in all directions. They are focused into a narrow cone in front of the jet, much like the focused beam of a lighthouse seen head-on. This means we catch a far more intense, focused, and energetic version of the jet's light than if it were pointed away from us. At the same time, the exact opposite is happening to the material on the far side of the jet, the part that is moving away from us at a similar incredible speed. Its light is stretched into longer, redder wavelengths and is drastically dimmed. Its energy spread so thin it becomes almost invisible to our telescopes. This intense beaming effect is why a blazar can outshine every star in its galaxy, appearing as a brilliant point of light from across the cosmos. It is not that the object is inherently more powerful than other quasars, but that its cosmic headlights are pointed directly down our line of sight, its relativistic motion amplifying its brilliance into a beacon we cannot miss. A galaxy's rotation holds a secret written in the speed of its stars. If the universe followed only the gravity of the things we can see, then the outer edges of a spiral galaxy should be moving far slower than the inner regions. This is the simple, elegant prediction of Kepler's laws, the same rules that govern our own solar system. Think of the planets orbiting our Sun. Mercury, the closest world, whips around at a blistering pace, while distant, cold Neptune drifts along in a slow, stately march. The pull of gravity weakens with distance, so objects farther from the center naturally orbit more slowly. For a galaxy, this logic implies that stars on the outskirts, far from the bright core of stars and gas, should be crawling along. Yet when astronomers measured these galactic rotation curves, they found something astonishing. The stars and gas clouds in the remote outer reaches were not moving slowly at all. They were orbiting just as fast as the stars closer to the brilliant center. The rotation curve was flat, a straight line of constant high velocity extending far beyond the visible edge of the galaxy itself. This was like discovering that all the planets in our solar system, from Mercury to Pluto, were somehow hurtling around the Sun at the exact same breakneck speed. Something was terribly wrong with the picture. The only possible explanation was that there had to be more gravity than the visible matter could provide, a vast and unseen source of pull. This invisible mass must be arranged in a gigantic spherical halo, enveloping the entire luminous galaxy like a ghostly cocoon. It is this dark matter halo that provides the extra gravitational grip, forcing those distant stars to maintain their unexpectedly high orbital speeds. Without this hidden anchor, the outer stars would simply fly off into the void, unable to remain bound to their galactic home. The silent, invisible presence of dark matter is not a minor detail. It is the dominant force sculpting the very motion and stability of every galaxy we see. The violence of a hypernova makes a standard supernova seem almost quaint. While a supernova marks the death of a star, a hypernova is its utter annihilation, an event so powerful it forges the most destructive beams in the universe. This cataclysm begins with a star that is not just massive but colossal and spinning at a ferocious rate. When its core finally runs out of fuel, it does not simply collapse into a neutron star. Its weight is so immense, its rotation so frantic, that the core bypasses that stage entirely and plummets directly into a black hole. The infalling material, carrying the star's incredible rotational energy, does not rebound in a spherical shockwave. Instead, it is funneled by intense magnetic fields into two narrow, ultra-fast jets that erupt from the star's poles at over 99.99% of the speed of light. These are not gentle outflows, they are diamond-tipped drills of pure energy boring their way out through the star's outer layers. The entire star is not just blown apart, it is unzipped from the inside out by these relativistic jets. It is this focused, blistering speed that links the hypernova directly to the long gamma-ray burst. The jets themselves are the source of that fleeting, universe-spanning flash of gamma rays. If one of those jets were, by chance, pointed directly at Earth, we would witness the birth cry of a black hole as the single brightest event in the sky since the Big Bang, a stark reminder that the greatest cosmic speeds are born from the most total destruction. Two faint, hazy clouds drift in the southern sky, looking like permanent fixtures of our galactic neighborhood. But these Magellanic clouds are celestial newcomers on a high-speed approach. Unlike the many ancient, shredded dwarf galaxies that long ago merged with the Milky Way, these two are likely on their very first daring pass. They are falling toward us at a tremendous velocity, a pace so swift it has, until now, acted as a kind of cosmic shield. Imagine a stone skimming across a pond. If thrown too slowly, it sinks immediately, but with enough speed, it skips across the surface. The Magellanic clouds are like that skipping stone, their high orbital momentum carrying them on a trajectory that has so far prevented our galaxy's immense gravity from grabbing and completely disrupting them. This initial infall means they are still relatively pristine, holding onto their own gas and their own distinct structures. Their speed has preserved their identity, but it also seals their ultimate fate. That very momentum is now carrying them not on an eternal orbit, but on a long, looping path that will inevitably bring them back. In a few billion years, they are destined to swing around and plunge directly into the Milky Way's disk. Their high-speed arrival will not be a gentle merger, but a violent, gas-rich collision that will ignite a firestorm of new star formation, forever reshaping our galaxy's appearance. These seemingly tranquil clouds are not placid companions, but high-velocity visitors whose first visit will also be their last. Even the most ambitious dreams of speed must confront the universe's ultimate law. But what if we could circumvent that rule not by moving through space, but by moving space itself? This is the radical promise of the Alcubierre warp drive, a speculative concept born from the mathematics of Einstein's own theory of general relativity. Imagine a surfer riding a wave. The surfer does not move through the water with their own power. Instead, the wave itself carries them forward. A spacecraft within an Alcubierre bubble would be like that surfer. It would sit at rest inside a local pocket of spacetime, a safe harbor while the fabric of the cosmos does all the work. The trick lies in manipulating spacetime itself. The theoretical drive would contract the space directly in front of the ship, pulling the destination closer, while simultaneously expanding the space behind it, pushing the starting point further away. The ship itself would not be accelerating at all within its bubble, and thus would not violate the cosmic speed limit. It would, in effect, be riding a wave of distorted spacetime, a warp bubble that could, in theory, propel it at speeds beyond light. This is not a conventional engine, it is a geometry engine using the universe's own fabric as its fuel. The mathematics are sound, a valid solution to the equations of general relativity, but the practical requirements are where the dream collides with reality. To create such a profound warp in spacetime would require a form of matter that does not exist in our current understanding of physics, something called exotic matter. This is not just rare or unusual material, it is a substance with negative energy density, something that would exert negative pressure, effectively having a repulsive gravitational effect. While certain quantum effects suggest tiny amounts of negative energy might be possible, the Alcubierre drive would require astronomical quantities of it to sustain even a small warp bubble. Furthermore, the energy requirements are literally astronomical, potentially equivalent to the mass energy of entire planets or stars. There are other theoretical hurdles, like the potential for the warp bubble to accumulate deadly high-energy particles during the journey, releasing them in a catastrophic blast upon arrival. For now, the warp drive remains a beautiful thought experiment, a testament to human ingenuity that shows us how to bend the universe's rules without technically breaking them. It stands as the ultimate speculative answer to the cosmic speed race, a reminder that the final frontier may not be about pushing against the void, but learning how to fold it. This final velocity dwarfs every other motion in the cosmos. In the very first sliver of a second, a trillionth of a trillionth of a trillionth of a second after the universe began, something impossible happened. The fabric of reality itself erupted in a growth spurt of unimaginable ferocity. This was the inflationary epoch, a period where space expanded not just quickly, but exponentially faster than light. The entire observable universe, all hundreds of billions of galaxies, was compressed into a volume far smaller than a single atom. Then, in a span of time too brief for any clock to measure, it inflated to perhaps the size of a grapefruit. To grasp this speed, picture a single atom suddenly swelling to become larger than our entire solar system, and doing it in less time than it takes for light to cross that atom's original width. This was not matter racing through space, it was space itself being created, stretching the very grid of existence at a rate that forever remains beyond any particle's reach. This incredible burst set the stage for everything that followed. It ironed out the wrinkles in the cosmos, leaving it smooth and uniform on the largest scales. It also magnified the tiniest quantum fluctuations, the random jitters of empty space, into the faint seeds of all future structure. Those microscopic ripples, stretched to cosmic proportions by inflation, became the gravitational blueprints for galaxies, stars, and ultimately, us. The entire cosmic tapestry, from the largest supercluster to the planet you stand on, finds its origin in that single, faster-than-light expansion. Every velocity we have explored, from the spin of a pulsar to the jet of a blazar, is a consequence of that first, ultimate speed. The universe began not with a slow creep, but with a shout, a definitive burst that wrote the rules for every motion that was ever to come. From the silent, constant sprint of a photon to the explosive recoil of a newborn black hole, our journey across the cosmic speedscape reveals a universe in perpetual, violent motion. We have raced alongside hypervelocity stars flung from their homes, felt the space-time tremble from colliding giants, and witnessed entire galaxies recede into darkness faster than light itself. Each of these velocities, from the subatomic to the supergalactic, is a direct consequence of the universe's fundamental rules. The speed of light is not merely a limit, it is a cornerstone of reality. The frantic spin of a pulsar is a testament to the conservation of angular momentum. The impossible flight of galaxies is the undeniable signature of an expanding universe. By studying these cosmic speed demons, we are not just cataloging astronomical curiosities, we are reading the operating manual of existence, written in the language of velocity. Every fact we have uncovered, from the time-warping jets of a blazar to the quiet, relentless drift of our own sun, is a piece of this grand puzzle. So, as this journey concludes, we turn the question over to you. Which of these 50 facts reshaped your understanding of the cosmos the most? Was it the ghostly rain of cosmic rays, the phantom kick of a rogue black hole, or the sheer, silent speed of inflation that sparked your curiosity? Share your mind-blown moment in the comments below, and if you are ready for more voyages to the very edges of our understanding, be sure to subscribe for our next exploration into the universe's